problem here where I don't think, and I'm just going to write this right here to save some time. I think this is a bad idea. If you squared the right hand side, you would get 275 also, But here, I think it's questionable. Theoretically, it's something you could try, but you'd end up with, when you square a trinomial, you get 9 terms. Some of them may be the same, but still, I don't think squaring here is a great idea, squaring both sides. Okay. Let me know if you can do it that way. Theoretically, you should be able to do it that way, but you might introduce extraneous roots, etc. I'm going to show you another approach here that's pretty neat. We're looking for positive natural numbers being positive integers. Zero is not allowed. Okay. Now, the nice thing about this radical is you do have a perfect square factor. This is what, 11 times 25 up here. So when you take the square root, you get 5 root 11. Now the cool thing about this, which makes the problem quite easy, or makes you see why squaring is a bad idea, is since you have 3 positions here and none of them can be 0, one try is going to be the 2, and the 1, right? So you see right here, this is just physical equality. We're not asking if anything's true. This is equal to this, which is equal to this. But you see, this begs you for the very clear solution. Y'all, I'm going to write these in ordered triple form. We'll write this x, y, z. And you see, you can literally just read off the answers here without being super, there's not too much to do in this problem, actually. Okay, so you would, your very first one would have to be this object squared, since this is the square root over here, right? So this would be 4 times 11, which is 44. Okay, would be the x coordinate, and then same thing again, 44. And then, of course, right here, you would just get 11. Now, notice this is symmetric in the sense it doesn't make any difference whether this is x, this is y, or whatever. You could permute these 3 factorial ways. And so you could also, this would be a solution. How do we want to do this? 11, 44, 44, and then maybe put 11 in the middle at the end here, right? I think of this as just one solution, but since this is a symmetric type of expression, meaning symmetric is a weird word to use here. It's just this could be y, this could be x, and this could whatever this could be whatever what I mean. So there's 3 factorial ways to do this, or no way, just 3 ways. I'm sorry, not 3 factorial. I guess this is 3 choose 2 actually, right, folks? 3 choose 2. So which would be 3. Or you could do it as 3 choose 1 because of the symmetry of the binomial coefficients. So in other words, these are, now you may think, are we done? Are we done? These are definitely solutions, right? Did I get anything back, which I don't think so. But also you can write 5 as 2 plus 2 plus 1, which is what I do, or 3, I'm sorry, 3 plus 1 plus 1, right? 3 plus 1 plus 1. And so in a similar fashion here, you would get x, y, z ordered triples, right? That's why you have to write the same solution 3 times here. Okay, so now right here, if you square this, you would get 9. 9 times 11 is 99. So you have 99 here. And then 11, 11. Okay, and then we'll do 11, 99, 11, right? And then the only other arrangement would be bring all the 11s to the front. Okay, so yeah, you can see there's 6 solutions here. We have 1, 2, 3 solutions here, and then another 3 down here. So there's 6 total solutions. It says what I said find. I should have probably said find all. Okay, but there are 6 solutions. And we found all of them. And by the way, if you were allowing for z, if you're allowing for just non-negative, you would have to deal with the 0, 1, 4 case, right? 0, 1, 4 would produce solutions if you were allowing for, and maybe there's others too, I'm not sure. But 3, 2, 0, right? Yeah, 5, 0, 0, or yeah, there's probably a lot of tries right there. So I just made it easier myself by making these positive integers. All right, and again, these are the solutions down here, these guys right here. Just by inspection, folks. Now, an interesting kind of speculation here, or not speculation, but an assertion. You're always going to have solutions as long as you have a square radicand, a radicand with a square factor. If mu, just food for thought, if you have mu, the Mobius function, mu at, let's call it n equals 0, that means it's square. Does that mean it doesn't have, or it does have a square divisor? Yeah. Mu at n, the Mobius function, means that there is a square factor that divides this, right? Now, and so as long as you have a square factor that divides it, you'll be able to factor out a nice integer and then split the thing apart, right? And so you'll have solutions there. But if mu of n is not equal to 0, there's no solutions, right? So at least I'm going to speculate. And it can only be 1 or minus 1 if you've ever seen the definition. I'm sure you have. But if it's not equal to 0, then I'm saying no solutions. And I'm talking about n being right here, the constant, the square root of the constant n, okay? No solutions. And I'm merely asserting it, but it seems fairly obvious, right? If you have a square factor, you get this kind of thing to happen, a square radicand. If you don't have a square factor, you would just be an irrational number. I don't think there'd be any solutions. Maybe there's irrational solutions, I'm not sure. But there definitely wouldn't, well, I guess there has to be a complex solution, but there definitely wouldn't be any integer solutions if you had this condition right here on the radicand constant. Okay. Again, here are the solutions right here. 1, 2, 3 of them. 1, 2, 3 of them. Okay.